right. Good morning, everyone. Welcome to today's class. Today we will talk about data management. We will use about 3 lectures to talk about this topic. There are 4 small sessions. Hopefully today we can finish the first 2 sessions. They are data wrangling. So what is data wrangling? Basically, it's the process of transforming your raw data to a clean and organized data set that is ready for future usage, for example, for machine learning modeling or for visualization, etc. And in this small session, we will cover all of the following topics: data exploration, how to manage one data frame, and how to combine 2 data frames or more data frames, and then grouping and looping. So in the first topic, we will talk about how to create a data frame by ourselves and how to describe a data frame to understand the features of a data frame, for example, the shape, and then navigating data frames. So this is the first topic. And then in the second topic, we will talk about a lot of details about handling one data frame. For example, how to subset the data frame, selecting rows based on position or some conditions, and how to manage columns. For example, how to select columns, how to drop columns, how to rename columns, etc. And in general, how to replace values in a data frame. Sometimes there are some values that are not correct, or you want to change the type of data, for example. And next one is how to handle missing values. So in this particular small session, we will only talk about one way to handle missing values. And in the last 2 sessions, we will talk more details about it. Okay. And then calculating summary statistics, finding unique values, etc. Okay. A lot of small topics in this part. And the third topic is grouping and looping. So we'll talk about how to group rows by some variables and how to apply a function over all elements in a column or in the entire data frame. Basically, we'll talk about how to use the apply function to manage your data in a more efficient way. Okay, and so the last topic is more than one data frame, how to concatenate and merge data sets, data frames. All right. So the most common data structure in machine learning is data frames. Data frames are tabular, 2-dimensional data. Rows are corresponding to subjects or individuals or observations, or in machine learning, in the computer science world, they call them samples. Each row is called a sample. Okay? In statistics, we say a collection of observations is called a sample. Okay? So it's two definitions of the same thing. Okay? And then, so let's take a look at a data frame, which is about passengers on the Titanic. So this is a public data frame. So let's load the data frame. First, import Pandas as PD, and then we will import the data from an online resource using pd.read_csv. This function is used to load CSV files, right? Okay. And then we show the first 5 rows. So it looks like this. A few variables: name of the passengers and passenger class, age, sex, survival status, whether or not the passenger survived or not, and then sex code. So apparently sex code and sex are explaining the same thing, describing the same thing, but they are coded in different formats. Sex is a categorical variable, and sex code is a numeric variable with 2 values, 1 and 0. So this is a data set. This is an example of a data frame, a two-dimensional. Each row is corresponding to one observation. Each column is corresponding to a variable, and the content is the value of the data. All right. So this is pretty much what I just said. Okay. And then let's first take a look at how to create a data frame by ourselves. So Pandas has many methods to create a data frame. In particular, we can do the following. So first, we can create an empty data frame. Just use the data frame function parentheses, then it's empty. We call it data frame 2. And then we can define each column one by one by ourselves. So for example, we first define a column called name, and then enter the values in this column. Suppose we only want to create a very small data frame with 2 rows, 2 observations, so 2 names. And then the corresponding ages of the 2 individuals. Right? And then whether or not the person is the driver in the car, for example. So it's a logical vector. So notice that in each assignment statement, we specify a list of values for each column. And then let's run this. So data frame 2 is a mini data frame, 2 rows, 3 columns. So this is a simple way to create a toy data frame by ourselves. So sometimes you just want to test a very simple model, or you just want to have full control of your data frame, then you can create it by yourself. So in the real world, we rarely need to create our own data frames. Usually we just import raw data from different sources. For example, last time we talked about how to import data from online resources and also from local folders, right? And we can import different formats of data, CSV, Excel, JSON. And after we import our data set, we need to understand the data, right? Let me see, I have a question. Can you also data wrangle with SQL? Yes, of course. But there are some Python packages that are very similar to SQL. The syntax are very similar to SQL. Actually, Pandas, the Pandas package, you will tell if you know SQL already, you will tell that many functions are very similar to SQL functions, okay, SQL commands, because Pandas is trying to imitate the operations in SQL. Consequently, Pandas is very efficient too, okay, in dealing with data frames. But we will not talk about SQL in our class because we have packages that are very similar to SQL. Okay? But definitely you can use SQL to manage data frames. Okay? All right, now let's see how to describe a data frame. First, you can show or view the first few rows. So we have seen this. The head function can be used to show the first few rows. By default, it will show the first 5 rows. Okay? And for example, the first 2 rows of Titanic looks like this. We can also show the dimension. Dimension is the shape, okay, number of rows and number of columns. So the Titanic data set has these many rows and 6 columns. It's a very small data frame actually. And you can also calculate some descriptive statistics for a data frame. So in Pandas, there is a function called describe. So Pandas data frames have this method, associated method called describe. And by default, it will only focus on numeric variables. So it will automatically ignore categorical variables. Categorical variables are variables with values that are character strings. So for example, if we call the describe method and apply on data frame 3, which is the Titanic data set, you will see this, you will get this table. So for each numeric variable, the function will calculate the number of valid observations, non-missing values. So for age, there are 756 of them, survival, and sex code. So these two variables don't have missing values, but age has missing values, a lot of missing values apparently, right? And it also calculates the mean and standard deviation for each numeric variable, and also the 5-number summary of them. So it's a very good way to summarize your numeric variables very quickly. Have a very quick look, and you can also see how many missing values there are. You cannot tell, actually, you cannot tell. Yeah, so this is just the number of non-missing values. You have to combine the information that you got from shape, okay, the shape function, to check if there are any missing values. And so this is a summary of what we have seen, the head function. And the tail function is similar to the head function, but it will show the last 5 rows by default. And just pay attention when you look at the summary statistics that you get from any functions, pay attention that some categorical variables are coded as numeric variables, like binary numeric variables. For example, sex code. Sex code is numeric. It has only 2 values, 0 and 1. But Pandas functions don't know that it is actually a categorical variable, so it treats it as a numeric variable. That's why it calculates the mean, standard deviation, and the 5-number summaries for it, although they don't make much sense for this variable. So in this case, it's better to either recode it, encode it into a real categorical variable or a factor variable, or you can use some other method to summarize this column. All right. The describe function actually can be used to summarize categorical variables too, if you specify include equals all, quote, all. So that means you want to describe all of the variables, including categorical variables. So for example, name, passenger class, and sex. So these 3 are categorical variables. So for categorical variables, the information that is provided by the describe function is very limited. You can see that it only provides a number of non-missing values and the unique values for the variable and the top category. Top category means the category that has the most observations, most number of observations, basically the mode of the categorical variable, the most frequent category. So apparently for name, the name variable, there are 2 rows corresponding to this person. In this case, Connolly, there are 2 observations. Similarly for passenger class, there are 4 unique values, and the top category is the 3rd class, which means this class has the most number of observations, the biggest frequency, which is 711. Okay. And for the mean and standard deviation and 5-number summaries, so it returns missing because, of course, we cannot calculate these for labels, like for categorical variables with label values, etc. So you can force the describe function to describe your categorical variables. However, the information provided is very limited. And a better way is to use some other functions. And another function to have a big picture of your data frame is the info function. Let's run this. So the info function will tell you the class of the object. So our data frame 3 is a Pandas data frame. And number of entries, which is number of rows, and the row indexes, and number of columns. And then for each column, it shows you the number of non-missing values and and the data type of the column. Object is kind of anything, basically is categorical. Is categorical. And float a real number. An integer is, integer, numeric integer. So you can have a very good idea about the entire data frame, right? Especially the number of non-missing values. So this is very important. For example, in this case, age has a lot of missing values. You can choose to delete observations with missing values in age. However, by doing so, we will lose a lot of data points. Right? We might not want to do it. In this case, we probably want to figure out a way to impute missing values in this column. If there are only a few missing values, for example, 1, 2, 3 missing values, then we don't bother to do it. We can delete it because we have not very small sample. We have 1,313 observations. It's not too small, so we can delete a few observations. We can afford that loss, but we cannot delete like hundreds of observations because we only have about 1,000. All right, so the info information is very useful. Now let's move on to subsetting data frames. So first, let's focus on rows. Selecting rows. We can select rows via location, just like what we did for matrices. There are two functions, the LOC function and ILOC function, location and index location. So the index location function can be used by selecting rows using the row indexes. For example, if we want to select the first row of the Titanic dataset, we can say this. We can use the square bracket 0. Okay, so this is the first observation. We can also select multiple observations at the same time. For example, the second, third, and fourth. And we can, if we know that we will start from the first observation, then we can omit the starting index, which is 0. Okay, so from 0. So iLoc function is very similar to some functions in R, okay, some other packages. And data frames do not need to be numerically indexed. You actually can use other variables as an index variable. So for the Titanic dataset, the name column is almost you can use it to identify rows. Right? It's almost 100% correct. Of course, in the previous slides, we know that there are some repeated values in name. Not a lot, maybe 2 names have repeated values. But still, it's a good option for index. So we can use the set index function to specify a new index variable. For example, we can maybe name, and after we run this, then the index is changed to the name column. And then you can use specific name to extract information about that row. Okay? So if you want to use the location function, LOC, you should refer to an index variable which is categorical with label values. So it works too. We rarely need to do it because usually there should be a row index already built in the data frame, so we don't have to specify an index. All right, so in summary, there are 2 functions that we can use to select rows according to their indexes. And most likely, we will select rows based on some conditions instead of just relying on positions. We probably want to use some conditions to select rows. For example, if we want to select observations that are female, we can do this. Just use the square brackets and put this condition in the square brackets. Data frame 3. The sex column is equal to female, quote female. Pay attention, you need to be very precise when you state the condition. Everything should be absolutely correct. Right? The variable name should be quoted, right? And S is capitalized, sex is capitalized. and female are lowercase, quoted. Right? If there is any error in this condition, then it won't work. And also pay attention, the sex column is not recognized, cannot be recognized by Python directly. You have to refer it, you have to say it's the sex column in the data frame 3 data frame. So this, and also I saved the result in a new data frame called df3f. This is the shape. So that is because for all Pandas data frames, whenever you do any operation on the data frame, the result will not be saved. It will not affect the original data frame, but instead it will create a new data frame. You have the option to save it or just print it. It's okay. If you, for example, you don't want to save it, you can get rid of this part. It will still work. You can see the output, the result of this operation. However, data frame 3 will not be affected. If you type data frame 3, the shape, everything will be the same, okay, as the original version. It will create a new data frame, but if you don't want to save it, it will be lost after this, you run the cell, okay? So this is the default behavior for Pandas data frames because it tries to protect the original data frame. And just keep that in mind. And we can also check the first 2 rows of this new data frame. Okay. All right. You can also specify multiple conditions, use multiple conditions. You just need to use this AND operator to connect them, combine them together. Okay. I believe you don't have to use parentheses to wrap the conditions, but I recommend you to use them because it will be very clear for you and for your readers, and it will avoid any confusions. Okay. So it's possible to use 2 conditions. So sex equals female and age is greater than 65. Only one observation satisfies this condition. So only one row is returned. All right, so that is select rows. Sometimes you want to delete some rows, but actually the operation is similar to those we used when we select rows. Just use some negating operations. For example, we want to select rows corresponding to male observations, then we can just delete those female observations. This is the same thing. Let's check the first 2 rows. Indeed, they are all males. And sometimes there are duplicate observations in a data frame. And definitely we want to avoid having duplications because it will mess up our model in the future. So if you want to delete duplicate observations, you can just take the data frame and call this drop duplicates method. So Pandas data frames have this associated method. And let's run this and check the shape of the new data frame immediately. Turns out that the new data frame has the same shape with the original data frame, which means there is no duplicate rows. Although we know that there are some duplicated names, right? So maybe the entries of other variables are slightly different, coded slightly differently, so that they are not treated as duplicates. See, the original data frame have the same shape. So from this example, you see that the drop duplicates function will only drop rows that match perfectly across all columns. So namely, it will only drop rows if it perfectly match some other rows. Right? In all of the values, all the same, then it is treated as a duplicate. row and will be dropped. Otherwise, it won't. Okay, it will just keep out everything. Right. And the related method is duplicated. Okay. So this one will return a Boolean series denoting if a row is duplicate or not. So namely, it will create a new column. So it will create a flag variable. So if it is duplicate, probably it will true, and otherwise false, etc. Boolean operator. And then let's focus on columns. Definitely you can select a few columns from a data frame. For example, I want to select these 4 columns. Notice that if you select multiple columns at the same time, you need to wrap them in a list. You cannot just do this. Then Python will give you some error. It cannot recognize it because you are inputting one argument, which is a list of column names. So a list of columns that you want to select. Right? So this is one object. It's kind of like column indexes. Right? And you run it. So this is a new data frame. Again, if you want to save the result, you have to name it, give a name. And you can also take a look at the first 2 rows. Deleting columns, there is a function called drop. So this one can be used to drop columns. I specify the column name and the axis. So in Pandas, axis equals 1 is corresponding to columns, and 0 is corresponding to rows. So it's the opposite with the definition in NumPy. Okay, remember, we talked about that before. But anyway, if you want to drop columns, specify axis equals 1. Then save the result in df3 v3. You see it has 5 columns now because 1 is dropped. So age is gone. So that is how to delete columns. You can also choose to delete multiple columns at the same time. Just remember, you need to wrap the column names in a list like this. And if a column does not have a name, which is very rare for Pandas data frames, but sometimes it might happen, right? Then you can drop it by its column index. So take the data frame and use the columns method to pull out the column indexes and specify the position. Right? 1 means the second column. Okay? And then df3 v5 will only have like 5 columns still, okay? And the second column is dropped. And sometimes you're not satisfied with column names. For example, in the Titanic dataset data frame, P class stands for passenger class, but P class is not very intuitive. People may not understand what it's about. You can create a new name for it. So you can just you call the rename function, and then use the columns argument, and then specify a dictionary for it. And the order is old name, colon, new name. So the new will be used to replace the old one in this order. So let's save the result in version 6 and then see the first 2 rows. You see, now it's called passenger class. Sometimes it's quite useful because sometimes the column names are not named very appropriately. Maybe they are very long or not very meaningful, or there are some characters that you don't like. You want to change them and rename. You can also rename multiple columns at the same time. Anyway, you just need to use a dictionary to wrap those pairs, right? Kind of like key value pairs. The key is the old name and the value is the new name, right? So just make sure that you pair them. See, old, new, and then use comma to separate them, and then old colon new. So by doing so, you can change the names of two columns at the same time. This is version 7 of the data frame. Passenger name and sex been changed. So we're done with renaming columns. Then how about the cells, the entries in a data frame? Sometimes you want to replace some values in a data frame. For example, if you don't like the term like female, you want to use woman to replace it. You can do it using the replace function. So this one is used to replace values, not column names anymore. It's used to replace values in a data frame. Sometimes you want to focus on a column. For example, I want to change female to woman in the sex column. So clearly specify the column you want to replace values and also the values. Okay? Still in this order, old, comma, new. Okay. And then let's run this. Let's see. So this is version 8 of the data frame. Okay, so this is the first two of, sorry. So since I only use the sex column, the sex column, so the result only has one column, which is sex. Okay? So now the values are replaced. Female is replaced by woman. So these are the first two observations. 0 and 1 are the row indexes. Okay, don't be confused. This is just a very small data set with only one column, the sex column. And you can also replace multiple values at the same time. You just need to specify a list of old values and a list of new values, and make sure the old values and new values are matched. So they are all matched. List them in the correct order so that they are 1 to 1 are corresponding. Okay, so after we do this, let's see that so both female and male are replaced by woman and man. All right, so this is the replace function. And sometimes you want to replace the entire data frame object by specifying the whole data frame instead of the single one. For example, in the Titanic data set, we know that there is a sex code. Sex code is binary numeric variable with two values, 1 and 0. Okay, and actually it should be a binary categorical variable, right? And also there is a variable called survived. And it is also coded as a numeric variable with 1, 0, two binary values, numeric values. And if you want to convert it to a sort of a factor variable with character string values, you can replace them too. Right? So in general, in the Titanic data frame, we want to replace the number 1 by the string 1 and 0 by the string 0. Right, so we know that 8 will be good. Right, so we can replace them at the same time. So in this case, we just take the entire data frame and replace 1, 0 by 1, 0. So then we save the result in version 10. And version 10 has the same shape with original data frame. So 6 columns and 1, 3, 1, 3 rows. And now you see survived and sex code have good character string values. A side note about this is that so it is good for visualization and some calculating summary statistics because survived and sex code are in the correct format. However, it is not good for machine learning modeling in Python because most of the models in Python only take numeric values. Okay, so you'd better create a new data frame and save the result like this and keep the original yes. Right? Still use 1 and 0s for survive syntax code. Because machine learning models in Python like numeric values. So they basically, most of them don't accept character string values at all. Okay? They don't know how to process them. Okay? Only accept numbers. All right, next one is finding unique values. Of course, it makes more sense for categorical variables because usually they only have a few unique values. For numerical variables, it's not that necessary because that is not what we really care about, right? So for sex, you see there are 2 unique values, okay, in the data set. Okay. The reason that we want to pull out unique values is because sometimes missing values are coded in a very weird way, very abnormal way. I use some special characters. Sometimes you will see people use 999 to denote missing values or -1 to denote missing values, etc. Okay. So this function can help us to identify those weirdly coded missing values, okay, or some special categories. And another way to find unique values and also summarize their frequencies is the value count function. So pay attention, there is an S here. This is a very useful function because for categorical variables, it will create a frequency table for you, basically a distribution table. You'll see male this many and female this many. Okay. A very convenient way to summarize the categorical variable. And if you want to calculate category proportions, you can add this argument, normalize equals true. Let's see, then proportions will be calculated for you, and sum is 1. Okay, so this is also very helpful for us to understand individual columns, categorical columns. Right? And Pandas also has this function, n-unique. So this one is used to calculate the number of unique values. So for passenger class, there are 4 unique values. So in the Titanic dataset, P class is indicating the class of passengers ticket. Okay. There are actually only 3 classes on the Titanic. However, there are 4 unique values. So let's use the value counts function to figure it out. It turns out that for one observation, the passenger class was coded as asterisk. Okay. So very likely that this is used to represent missing value. So that's why the value counts function, the unique function are very useful for us to understand categorical variables. In particular, you can recognize some special extra categories that you don't expect to see, and you need to figure out a way to handle them. Okay. If you only have one observation in this case, you can choose to drop this observation or use some simple imputation method to impute this missing value. Okay. It will not affect the result that much because we only have one observation. But if we have a lot of observations like this, for example, 500, then you should figure out a way to impute the value. Okay. And then handling missing values. So it is a very common problem in data wrangling. It's not always true that a data frame is clean. Usually they have a lot of missing values. There are 2 functions that can help us to filter out missing values directly. So of course, this is the easiest way, the most straightforward way. However, it might not be the best way, of course. Okay, just pay attention to that. We just start from the easiest and it may be the worst way. So let's see, there are 2 functions, is null and not null. Suppose we want to get rid of all of the observations with missing values in sex. We can do this. Data frame 3 sex dot not null. So this function will return logical values, true or false. So if it is true, then the row will be kept in the result, otherwise not kept. So not null is true means the value is not missing. So it will get rid of all of the observations with missing values in sex. So this is one way. Sometimes you want to examine those observations with missing values in some column. For example, we want to study those observations with missing values in age. We can do this by data frame 3 age and dot is null. So this one will also return logical values, true or false, but it will return true if it's missing. So eventually it will choose rows with missing values in age. So this is version 13 of the data frame. And then you can do some more calculation, summary job for this data set to better understand those observations. Right. So see, age has missing values. All of them values in this column is a missing value in version 13. All right. And actually, pandas often use missing values. But it is not defined in pandas or in base Python. So in order to specifically call or use a missing value, you need to first import the NumPy package. So import NumPy as NP, and then you can call the missing value defined in NumPy, which is np.nan. So this is a valid value, which is used to denote a missing value. For example, you can replace all male by missing value. Of course, this is an absurd operation. Just this example just let you know that it's possible to use a missing value as a valid value to replace something or to do something else. Right? So it's, of course, this is an absurd operation. We should never do it. Okay? We should never replace a valid value with a missing value. Makes no sense. Just an example. And then calculating descriptive statistics. So previously we have learned some summary statistics, some functions like describe, right? But Pandas has some more functions specifically for mathematical operations or statistics calculations. For example, the max function, mean function, average, and sum and count. Okay, so they are all available in Pandas. You can use them if you need. If you don't want to directly call the describe function, you are interested in some specific statistics, you can use them. There are many more. You can just Google the Pandas documentation and you see many more functions available for you to use. For example, the variance function, standard deviation function, kurtosis, skewness, SEM. This is kind of useful. Standard error of the mean, which is by definition as divided by square root of n, and standard error. And also mode. So this is the most frequent category. Yeah. So all of them are available in Pandas. So in Python is very interesting. Different packages have different functions. Sometimes they overlap, right? But they may have different features. Even if they have the same name, they may have different features. So that's why when we import packages, try to import the package explicitly using the first method. So last time we talked about it. You can apply a function on the entire data frame, then it will apply it to every column of the data frame. So, sorry, any questions so far? Then let's move on. Sorting data frames. So this is also a very useful and common practice in data management. You want to sort the entire data frame according to a variable or a few variables. The function we use is, or the method we use is sort values. There is an S here. Pay attention. There are a few arguments by. So this is a column name or list of column names to sort by. And then axis to sort, 0 for rows and 1 for columns. Usually we sort observations, so it should be 0. We rarely sort columns, okay? It's not very helpful. And ascending, by default, it should be sorted in ascending order according to some variable or a list of variables, but you can change it. If you say ascending equals false, then it will sort in the descending order. And in place, so this is an argument that you can use to change the data frame in place right now. So instead of returning a new sorted data frame, it will just work on the original data frame and change it. So actually this in place argument is available in many methods. Actually, you can choose to do it to change the current data frame. However, I don't recommend you to use it frequently because you'd better keep the data frame intact. Okay. What if we do something wrong, very bad, and then we will ruin the data frame? We don't want to do that. So keep the original data frame intact. It's important. Okay. But sort, sometimes we want to sort it. So let's see an example. Suppose we want to sort the Titanic data frame by class. And X is equal 0, that means we sort it along the rows. And in plus equals true, that means we will actually change data frame 3. Let's run it. Now you see, indeed, data frame 3 has been sorted, changed. See passenger class, according to passenger class, start with asterisk, and then first class, and then second and third. For numbers, it's just in ascending order. For character strings, it will follow the alphabetic order. All right, so this is the last slide in this small session. We talked about a lot of topics, very small topics, but they are very useful, like practical skills. Got it? Question? Does Python utilize the pipe operator similar to R? Yes, there is pipeline. We'll talk about it a little later, but usually it's not used for data wrangling. It is used to build a pipeline for machine learning. Usually it will start with read the data and then pre-process the data and then use some machine learning models to fit the data. Okay, so usually the pipeline is used for machine learning, not for data wrangling. Yeah, I have never done this. You use pipeline. I have never used pipeline to do data wrangling. Maybe it's still possible, but pipeline is a function in scikit-learn. I think it's a machine learning function. All right. Good question. All right. Any other questions? Great. Let's move on to the second small session in this module, data wrangling 2. So in this small session, we will discuss grouping rows, looping along columns, and handling two data frames. So first, group rows by values. So far, when we summarize the data frame, we just treat it as one object and do everything on the entire data frame or the entire column of the data frame. But actually, we can group the data and calculate statistics for particular groups of the categorical verb. So let's load the Titanic data set again. And then suppose we want to compare the average set, the means of all of the columns for each sex group. Right? We can do this. Group data frame 3 by sex, and then we can call the mean function. Now let's see what we get. So then this small table is returned. So apparently the mean function will automatically ignore categorical variables. For example, name and passenger class, it automatically ignores them and only calculate the average or the mean for numerical variables, age, survived, and sex. The point is the data is first grouped by sex so that you can compare the mean age between the two sex groups and the survival probability for the two sex groups. Okay, for example, female passengers had a much higher survival rate compared to the male. And sex code mean and female and male. 1, 0. I think it's rounded somehow. It's rounded. All right. Now let's move on to next slide. So group by is where data ranking really starts to take place. It's common to compare some summary statistics among groups. For example, you might want to compare the survival probability among the 3 passenger classes, right? Since so focus on survived, so you see that the first class has the highest survival rate and third has the lowest. So you can kind of write your observation. Based on this observation, you can write a story about it. Okay, try to understand why it is true. Okay, unfortunately. For beginners, it's common to write a code like this. I take a data frame, group by something, and you expect to see something, but actually nothing will happen. Right? Just say, okay, you try to group by it, but nothing will be returned. Right? That's because the group by function must be paired with some operation. For example, mean, standard deviation, etc. Okay? Otherwise, you will not do anything. And you can use this function to compare some summary statistics. Okay? For example, how many survived, how many died, using the count function. Or you can study the relationship between two categorical variables and the response variable survived, okay, by doing this group by two categorical variables, passenger class and sex. Then within each class, you can study the relationship between male and female group, right, the survival rate. And you can also reverse the order. So first, group by sex, and then passenger class. Then you will see a different dimension. Right? In the female group, which class has the highest survival rate, which class has the lowest. And whether or not the pattern is consistent among the two sex groups. So this is another story, okay? Another way to explore your data and create some hypothesis sometimes, right? Based on some more statistics, you can have some hypothesis, and later on you can use machine learning models to verify it. Of course, we can also group the data by two variables and call the age column and describe it. So by doing this, you can compare multiple summary statistics for a numerical variable for different groups of data. So it's also a very good way to study the relationship between categorical variables and numerical variables. This is especially useful if your response variable is a numerical variable, and you want to see which categorical variables has very big influence on the response variable. So a very good way to show it. All right. Now let's move on to looping over a column. You have the option to use a for loop, for example, to print out something in the column. That means you are looping along the column. Looping means starting from the first observation all the way to the last, a fixed loop. So for example, for name in the first two names, 0, 1, I print the uppercase name. Apply the upper function on the name and then print it. Yeah, do this. It works. So, however, as I said previously, looping in explicit loops in Python are very slow. So if we can avoid it, we should avoid using a for loop or while loop. Instead, we should use implicit loops. In Python, we have a method called apply. So this is very similar to the apply family of functions in R. I believe Python imitates apply functions in R. So it creates this apply function in Python as well. So it will apply the same function on each item or each column or each element in a vector. So let's see how it works. So we first create a function called uppercase. It will take a string and call the upper function to make it uppercase. Okay, so call it uppercase. And then this function is defined. After this, we can apply it on all of the components in this column, in the name column. And of course, I only want to extract two of them. So this will essentially do the same thing that we did using the for loop. Okay? However, this one is more efficient. It's supposed to be more efficient. So you might wonder, why don't we just put upper here? That's because this upper is not a function. It's a method. It's a dot method. You cannot directly put a dot method here. It must be a real function. You can define it by yourself. You can also apply a function by a group. So first, group the data by sex, for example, and then apply a lambda function, calculate the count. So see, this is an example of using the lambda function to create a short anonymous function. So see, this function is created and used right away without a name even. So let's see how it works. So basically, it will calculate on the non-missing value, number of non-missing values for each variable for each sex group. So we have this nice looking summary. So this is an example of using the lambda function. But basically, the apply function can be used to apply an existing function on anything, a grouped data or a column, etc. And the function can be created right away within the apply function. You call it using the lambda. And yeah, alternatively, you can, if you don't want to use the anonymous function, we can create a new function called CT. It stands for count. And then it takes only one argument, and we apply the count method on the argument. So then we can use it right away by the same result. If you don't want to use a lambda function, you can use the def function to create a real function, a regular function. Then let's move on to handling more than one data frame. So first, concatenating data frames. Concatenating means just combine them together, join them together. Two directions. You can concatenate two data frames vertically. Essentially, you will stack two data frames vertically like this. Okay. So in this case, of course, the two data frames should have similar columns. Otherwise, it doesn't make sense to stack them because then each column will have different variables. Okay. The function is called concat, and x is equal 0 means concatenate along the row axis. And okay. Let's see one example. We first create two small data frames. The DFA look like this, okay? 3 rows and 3 columns, ID and first name and last name. So very simple data frame. This is called DFA. And then the second data frame called DFB, it also has 3 rows and 3 columns, okay? ID first and last. And ID have 3 different values for classes. So apparently DFA and DFB have exactly the same columns and column names. So they are kind of like two parts of a data set. Maybe one is old data set, one is new data set, a new data set. Then it makes sense to concatenate them vertically. The syntax is like this. The concat function is in Pandas. So don't forget to refer to the library. And then use a bracket to wrap the two data frames you want to concat together and specify the axis. And then this is the result. Again, we didn't save the result, so it will be gone after we quit Jupyter. If you want to save the result, name it, give a name, and assign it. So this is how to concatenate two data frames vertically, okay? Stack them. And you can also concatenate two data frames horizontally. You just need to specify axis equals 1. That means along the columns. So our DFA and DFB have the same number of rows, 3 rows. So it's actually very convenient to concatenate them together. So Python allows it, no problem. However, you see, the result is not so good because now it is not a tidy data frame anymore because each row is not corresponding to one observation anymore. It contains information from 2 individuals, and it's quite messy. It looks neat, but it's quite messy because you cannot analyze them in a good way. So instead of concatenating data frames horizontally blindly using the concat function, a better practice is to use the merge function. The merge function is similar to the different joins in the R package dplyr. So again, this is also similar to some function or commands in SQL. You will see. Let's take a look. So we first create a data frame called a df employees. It has 4 rows and 2 columns, employee ID and name, very simple. And the second data frame called df sales. So this one contains the information of employees' total sales, so employee ID and total sales. So apparently we have a main data set and a data set which provides some supplementary information. So it makes sense to merge them horizontally. To merge them, we can call the merge method function in Pandas. Just list the 2 data frames you want to merge, and then lastly specify the column that you use to do the matching work. So apparently both of DF employees and DF sales have the same column called employee ID. Naturally, this should be the column. And by default, the merge function will do an inner join. Namely, it will only contain or keep the observations with matching values in the unvariable. So in this case, only 3 and 4 are kept in the result because 5 and 6 are not contained in the employee data frame. And 1 and 2, employee 1 and 2 are not in the sales data frame. So only the observations with matching values in the employee column are kept. So this is the default behavior for the merge function. So there are 4 joins, 4 types of merges or joins in Python. So this is very similar to the join functions in dplyr. So inner join default, outer join. So this is the most generous one, which will keep everything intact. It will not delete any observations, no matter there is a matching p-value or not. Left join will keep the left table complete. And right join will keep the right table complete. So these are the definitions. For example, left join is commonly used in practice because it will keep the left table complete. So usually when we do merge jobs, one table, one data frame is considered as the main data frame. And we have some metadata, some additional data frames. We want to add some more information, more columns to the main data frame. So we always want to keep the left one data frame intact, complete. We don't want to lose any information from the main data frame. Then we should use the left join. So the right table in this case will not be kept intact. Okay? Only rows with matching values in the unvariable will be retained. And the missing values will be filled if needed. Let's see some examples. So let's first do an outer join. Outer join is the most generous. You'll see it will not lose any information. This is the left table. A right table are employee and sales. So 3, 4, 5, 6. They are also there. Right? So it's the most generous one. If you don't want to lose any information, use an outer join. And if we use a left join, by the way, the argument is called how. If we do a left join, you see the left table is complete, but the right table is not. Employee 5 and 6 are removed because they don't have matching employee IDs. And right join will keep the right table complete. 3, 4, 5, 6 are kept in the result, but 1 and 2 are gone because the left table has 1 and 2. Don't care the left table. And lastly, sometimes when we join 2 tables, the 2 tables have different names for the matching variable. For example, let's manually change the column name of the employee ID from the original name to ID itself and call it DF sales 2. Okay, so now in DF sales 2, the employee ID is just called ID. But in the first data frame, it's still called employee ID. So now they have different names. So it's not a big problem because you have the option to specify the left on variable and right on variable. In the left table is in the DF employees table, the ID is called employee ID. So left on equals this. In the DF sales 2 table, the ID is just called ID. It doesn't matter, right? And then let's do a left join. We get this result. And notice that there are 2 ID columns. It will not automatically remove the redundant column. If you want to drop it, you can just add a drop method at the end. Then no repetition will be good. All right, right. All right, we are done with the first 2 sessions in data management, which is great, very neat. And tomorrow we will start to talk about how to handle numeric data. We will zoom in the issues we need to take care for numeric data. In particular, how to pre-process numeric variables and how to deal with missing values in numeric variables. All right. If you have any questions, you can stay. Otherwise, I'm free to go. See you guys tomorrow. Bye. Good morning, everyone. Welcome to today's class. Today, we'll continue to talk about data management. And today, we will finish session 2.3, handling numeric data. So let's see the topics in this section. So in this section, we will talk about strategies for transforming raw numeric variables into features for machine learning algorithms. Because machine learning algorithms usually are quite complicated and it's really difficult to converge. So they really like kind of like restricted values, values that are scaled and processed so that values are within a certain range, or the values have a certain mean or standard deviation. So basically very kind of like normalized data. So we'll talk about how to process numeric data today, and tomorrow we'll talk about how to process categorical data. So these are the topics today: rescaling features, and then generating polynomial and interaction features. So sometimes this is also useful. And then transforming features. Basically, we want to transform numeric data into continuous numeric data into discrete numeric data, sort of like ordinal data. And then how to deal with outliers. This is not exactly transform. This is not exactly discretizing data. This is another topic. So this is about using some math function to transform data. Okay? And lastly, how to handle missing values. All right, let's start from the beginning. Rescaling feature. So rescaling is very common in pre-processing task in machine learning. So many of the algorithms assume all features are on the same scale, right? Typically between 0 and 1, or -1 to 1, or they have some certain features. Okay? So we will talk about 4 scaling strategies or techniques: right? The min-max scaler, standard scaler, robust scaler, and the normalizer. So first, the min-max scaler. So this is the formula. Xi prime is the processed transformed value, and is equal to xi minus the mean of x divided by the range of x. In this formula, x is a vector. So let me make it clear. Use different color. So this x is a vector. For example, we have n observations. Okay, this is a vector. And to min-max scale any observation in this vector. Okay? So xi prime, so you minus the mean of it and divided by max minus the mean. Okay? Basically the range of it. Okay? So let's examine, study the range of the transformed data, x prime. So consider 2 extreme cases. If xi is equal to the minimum of x, then what happens? Xi prime will be equal to 0, because the numerator will become 0, right? And this is one case. Another case is another extreme case. Xi is equal to maximum of x. Then you see the numerator will become max of x minus mean of x, right? then xi prime will equal to 1. The numerator and denominator are equal. So the transformed data value xi prime will be equal to 1. So these are the two extreme values. And in normal cases, xr are in between min x and max x. So consequently, the transformed value xi prime must be in this range, okay, from 0 to 1 inclusive, right? So this is called a min-max transformer. After you transform the data, the vector, all of the values are between 0 and 1. If it's a one-dimensional data set, right, then all of the values are this range, in this range. Okay. If it's two-dimensional, then the transformed values will be within a unique square. Suppose there are two features variables, for example. Then all of the transformed values will be within this unit square. So it's quite restricted, okay, in a very small region, right? So this is min-max. The next scalar, let's take a look at an example. So we load the Titanic data set again, right? And now we'll focus on the age variable. Age is numeric, right? Then let's use the min-max scalar to rescale the feature age. Okay, so first, load the submodule called Preprocessing from scikit-learn. Okay. And then we first create a scalar, or you can say we instantiate a scalar. Instantiating means create some method or object with some parameters specified. So let's create a scalar. Use the min-max scalar function and specify the range. Feature range is 0, 1. So I believe this is also the default range, but you definitely can can transform the data into different, within different ranges. For example, you can let it be between 1 and 2, or -1 to 1. Okay? You just need to change these two values. All right, so this is a scalar, right, with some parameters. Then we can call the fit transform method to transform the age column and save the result in scaled age. And then let's run it and extract the first three values in the transformed age column. Right? So these are the three values. So they are all within the range between 0 and 1 in this interval, right? So notice that I use 2 layers of square brackets here because I want to make it a column vector. Okay, if you use single bracket, I think you will get a row vector. Anyway, this is an example of using min-max scalar to scale your data. And notice that we use fit transform, but actually there are 2 options to scale a feature. One way is to first call the fit method to calculate the min and max values of the feature, and then use the transform method to rescale the method and rescale the feature. So basically, you can do it separately, fit and transform, or directly call fit transform. Mathematically, there is no difference. However, when we talk about machine learning, you will see that we will prefer the first option. Okay? That is because usually in machine learning, before we even start training the data, we split the data to 2 parts: a training data set and a test data set. Right? So usually when we pre-process data, we will apply the fit method on the training set and calculate necessary statistics. And if we use min-max scalar, we will calculate the mean and max for each column, for example, and save it. And then we call the transform method to apply it on the training set, and also use the same scalar with the same mean and max that are calculated from using the training set to transform the test set. That is because, remember, our model will be trained using the training set. So consequently, our test set is assumed to be in the same same population with the training set, and the model is fitted using the training set. So it will be better to use the mean and max, the parameters that calculated from the training set to scale our test set. Okay, so that the test observations are assumed to be from the same population of the training set. So at that time, it will be quite different. Right? For now, it doesn't matter, right? Because we are not there yet. We're just talking about scaling. So for now, we can just directly call fit transform. And this fit method will calculate some parameters. It really depends on the scalar or the model you are using. If you use, for example, the next scalar, the standardizer, okay, then the fit method will calculate the mean and standard deviation of each column. Okay, so it really depends on which scalar, which model we are using. The fit part will calculate some parameters, okay, statistics. Okay. And the second scalar is standardizer. So it's similar to calculating z-score. Okay. Again, so this x bar is the mean of the column, okay, the column vector x, and s is the standard deviation of the vector. So calculated xi. So after the transformation, then the mean of x prime will be 0, right? And the standard deviation, the variance of x prime will be 1. So it's kind of like a standardization process. So this is called standardizing. So let's transform age using the standard scalar. So first, let's instantiate it and call it scalar 2. And notice that we just use default parameters, and call the fit transform function method and apply it on the age column. And then we pull out the first 3 values. So notice that after we standardize the values are not bounded. However, the mean and the standard deviation are fixed. The mean is equal to 0, the standard deviation is equal to 1. But there is no lower bound and upper bound for the transformed values. Okay? So this is standardization. And then after we do that, let's test if the mean of the transformed data, standardized data, is indeed 0. If we just directly apply the mean function, you will get a missing value. So that's because, remember, age has a lot of missing values. Okay, and after you transform the data, there are still a lot of missing values. And the mean function will not ignore missing values automatically. To fix that, we can use this function instead, NaN mean. So this function will automatically ignore missing values and calculate the mean for our non-missing values. So see, the mean of the standardized age column is equal to this. Not exactly 0, but very close to 0. So this is negative 1.88 times 10 to the negative 17. So this means 10 to the negative 17. Okay, so 1.88 times. So it's very close to 0. Okay? So it's not exactly 0 because it is due to some rounding error in the calculation process. Okay? So in concept, after we standardize the data, the mean of the column should be 0. Okay? We can also verify that the standard deviation is 1. Standard deviation is good. Okay? It's exactly 1. So this is the second scalar, standard scalar. So what's the difference? The min max scale values are between 0 and 1, so they are bounded. So basically, after you use the min max scalar to process your data, the mean and the max of each column are fixed. Okay, mean is 0, max is 1. Right? So 2 statistics or 2 parameters are fixed. And if you standardize your value, then the mean and standard deviation will be fixed. Mean is 0, standard deviation is 1. But minimum and maximum are not fixed. So standardization is more common to use for machine learning pre-processing. However, it really depends on the learning algorithm. For example, principal component analysis works better using standardization, right? PCA. So this is an unsupervised learning method. It prefers standardizing. But neural network likes min-max scale data more. Right? So it really depends on the model that will use the data. All right. Then sometimes if your data is quite normal, right, namely is roughly speaking symmetric, or at least is unimodel and is not severely skewed, then the mean and standard deviation are good quantities to measure the center and the spread of data, right? So if the data is relatively symmetric and not skewed, then mean and standard deviation are good measurements of the center and the spread of data. However, if your data is very skewed, then mean is highly influenced by extreme values, outliers, and also standard deviation is also, because both of them will use all of the observations in your data set, all of the values in each column. So they are highly influenced. In this case, if your data is very skewed, it's better to use robust measurements of center and the spread. The robust measure of center is the median. It will measure the true center. And the robust measure of spread will be interquartile range, which is the third quartile minus the first quartile, right? Because quartiles are not influenced by outliers, right? So this is the 75th percentile, this is the 25th percentile. So there is a scalar called robust scalar, the robust scalar. So instead of subtracting mean from each observation, we subtract the median from it. Right? So use the median to measure the center and divide the whole thing, the difference by IQR, interquartile range. So this is called the robust scalar. Right? We use IQR to scale the data, use mean to center the data. Okay? So consequently, this is more robust to outliers. So if your data is not very normal, then use the robust scalar. Okay. So let's see how to run it. So we first create a scalar, call it scalar 3, right? Robust scalar. This is also in the pre-processing submodule in scikit-learn. Right? Then fit transform age. Let's pull out the first 3 rows. And it's not bounded. Okay, it's not bounded, just like the standardizer. Okay? It's not bounded, but the median should be 0. Right? The median should be 0 because you see in the formula we subtract the median from each observation. Consequently, the median should be 0. Right? You see. And by the way, we should use this function NAN median because there are missing values in the processed data. Right? So this is a robust scalar. The last one is a normalizer, normalizing observations. So far, the 3 scalars we talked about focus on columns. And notice that it's in the fitting part. Okay, it will calculate some statistics for each column. If we use min max, we calculate mean and max for each column. And for standardizer, we calculate mean and standard deviation, use them to scale the data. And for a robust scalar, we calculate the median and the interquartile range. Okay. So all of them are about a column. Okay, so it will calculate these statistics for each column individually. So focus on column, and then use these statistics to scale or process each column respectively, right? But normalizer is different. because it will rescale. It will focus on rows. It will focus on rows. So it rescale the values on individual observations to have a unique norm. So instead of focusing on columns, it will focus on rows to make sure that the norm is equal to 1 after we process the data. So what is the norm? There are different types of norms. The most commonly used one is the Euclidean norm. It's defined in this way. Square root of x1 squared plus x2 squared all the way to xn squared. So here x is a vector again. So let's clearly define it. So and the norm is the square root of sum of squares of all of the values. Right. So this is an L2 norm called L2 norm. Now how to process transform the data? It will divide each observation by its row norm, and then call it x prime. So let's try to understand the scheme and why after the transformation, the norm of each row will become 1. Let's go back to the previous slide. I created an empty slide for derivation purpose. So let's clearly define everything. X is the features matrix. Suppose there are P columns. And suppose we have n observations in our data set. So this is a feature matrix, a regular feature matrix with n observations and P columns. Right? Then normalizing will focus on each row. Right? Let's calculate the transform norm. Right? So for example, x2, let's focus on the second row. x2j will be equal to x2j divided by the norm of x2, right? Where the norm of x2 is square root of x21 squared all the way to x2p squared. Okay. All right. We do the same thing for each j. J is from 1 to p. We do the same thing for each number on the second row. Right? Then after the transformation, let's verify that the norm of x prime, x2j primes will be equal to 1 after transformation. Right? So x2 prime norm by definition is equal to x21 prime square plus x2 prime square all the way to x2p prime square. Okay. And x2j is defined in that way, so let's calculate it. So x2j square divided by x2 norm square plus all the way to the last one is x2p prime square divided by x2. Sorry, no prime anymore. In the formula, that should not be prime. So like that. Oops, did that too. In the formula, there should not be prime. Oh yeah, it is. There is prime. Sorry. Okay. So here there should be no prime. Yeah, there should be no prime. Anyway, sorry. So then you add all the numerators together. What we'll get? Oops. if you add the numerators together, you will get x2 prime square, right? Exactly, the definition is here, and the denominator is also x2 prime square. Oops, that too. So it's 1. Sorry. All right. So we have proof that after transformation, the norm of each row will become 1. It will become 1. Okay, it's very clear, right? And then, for example, if you have a two-dimensional features matrix, right? Two-dimensional features matrix. Consider the transformer data x1 square, x2, x1, x2 prime, okay, after the transformation. After transformation, okay, let's consider a particular point. Then measure the distance between the point to the origin and call it the radius, right? The radius. So by definition, is equal to x1 square, square root of x1 square plus x2 square prime square. Okay? And we know that after the transformation, the norm is equal to 1. Okay, so this is exactly the norm of this vector, okay, or point, okay, is equal to 1. So consequently, after you normalize your data, all of the transformed observations or data points will be on a unit square. Unit circle. They might be positive or negative, but the distance, which is the norm, right, the L2 norm, is always equal to 1. So if you have two-dimensional data, after you transform the data, they will be on a unit circle. Unit circle. All right. Sorry about that. My derivation is a little bit how to say bumpy. Sorry. All right. So this is normalizing. So the key point is we are transforming data along the rows. Okay? And after the transformation, the norm of each row is 1. Right? That's it. Okay, that's the key point. Let's see how to do it. So first import the normalizer from preprocessing. So now we will create a smaller features matrix with only 2 columns. And we first create the normalizer, choose norm to be L2, which means we are using the Euclidean norm. Okay? Euclidean norm, call it normalizer 2, and then directly transform the features matrix. Okay? So see, this is the transformed features. You can verify that you square the first term and square the second term and add them up, it should be equal to 1. And take square root, it should be equal to 1. Okay? You can verify it easily. And alternatively, you can use L1 norm. Okay? So L1 norm is the sum of the absolute value of each values in a vector. Okay? So to do it in Python, we can just specify this argument norm equals L1. Okay? Call it normalizer 1 and transform the features. Okay? Then after transformation, the sum of the absolute value of the values in each vector is equal to 1. So now this is very obvious. 0.5 plus 0.5 is 1. All of them are positive anyway. Originally they were positive, so that's why they are also all positive. The sum of them is always equal to 1. Right? All right, so this is another way to normalize your data using L1 norm. So L1 norm is also called Manhattan norm. So this is a summary of all the rescaling strategies. Standardized scalar. So this is for, so after we standardize that, we ensure that for each feature, the mean is 0, the variance is 1. And the robust scalar works similar to the standard scalar, but it ensures the statistical properties for each feature that guarantee that they are on the same scale. However, robust scalar uses a median and interquartile range instead of standard deviation. And min max after the transformation, then the mean will be 0, the maximum is 1. And the normalizer will ensure that the norm of each row will be equal to 1. Let's take a look at this diagram, this plot, to sort of compare these 4 scalars. So this is original data, two-dimensional, x1 and x2, only two-dimensional. And x1 is between 10 and 15 originally, and x2 is between 0 and 10. Right? So in this kind of rectangular region. Right? And we color them using 2 colors, red and blue, so that we can visualize the change of these 2 groups of observations in the transformed data set, right? So that you can have a better understanding of the effect of transformation. So standard scalar, after you standardize it minus the mean divided by standard deviation, so the data will be kind of like within a circle, right? Like a cloud, circle cloud, right? But there is no boundary, right? There's no specific boundary. And robust is kind of similar to standard scalar, but it's more like somehow like a diamond shaped region, right? But still not bounded actually. And min max, as we have I have demonstrated, if you use min max scalar for 2-dimensional data, after the transformation, they will be within this unit square. And lastly, normalizer. After we normalize the data, all of the transformed observations will be on a unit circle. And the reason that for our data is in this region is because both x and y are positive. x1 and x2 are positive, right? So that's why after you transform them, they are also positive in this region. But they are on this unit circle. All right. Any questions? Any questions so far? Okay. So next topic is generating polynomial and interaction features. Sometimes, for example, if you fit a regression model, you have some feature variables, and you suspect that there is a kind of nonlinear relationship between some variables and y, then you might want to add higher order terms like square, or if you think 2 features are related, right? There is a kind of correlation between these 2 variables. You want to add an interaction term. So it's very convenient to do so in using the scikit-learn functions. So it's just called polynomial features. So we import this function, and then we create a very small feature matrix, 2 columns, 3 rows, because this is easier to for us to observe the result. Right? We just create a very small features matrix. Then create the function, instantiate the function. So degree equals 2 means the highest order term in the polynomial will be square. And include bias equals false means I will not add a column of ones to the features matrix. Remember in regression, for example, a linear regression with 2 variables. If you allow intercept, like the bias in it, then in the data matrix, there should be a column 1 added, right? Because this is corresponding to the first coefficient, the intercept. Right? So beta 0 is essentially beta 0 times 1. So you have the option to add a column 1, but we will not, because we actually don't need it. include bias equals false means that we will not add the column 1. So now let's see what happens. We use the polynomial interaction too. So this polynomial features function and fit transform our features matrix. You get this. Okay. Initially, we have 2 columns, and after we apply the function, we have 5 columns. So this is x1, apparently, right? And the second column is the original column x2. Then the third column apparently is x1 squared, right? And then what is this? This is apparently x1 times x2. And the last one is x2 squared. So it will always follow this order. x1, x2, and then x1 squared, the interaction between x1 and x2 and x2 squared. So always in this order. If degree equals 3, right, you allow cubic terms, then you will have a larger matrix, features matrix. You will follow this order. First, degree 1 terms, and then degree 2 terms, then degree 3 terms. So the sum of exponent is the degree of the term. For example, x1 squared times x2, this has degree 3 because 2 plus 1 is 3. Similarly, interaction. So this is a degree 2 term because 1 plus 1 is equal to 2. So this is a very convenient way to create polynomial terms. Sometimes you don't want to add square terms. You only want to add interactions. Then you can just add this argument. Interaction only equals 2. So then let's see x1 and x2 and x1, x2 will be in the result. And x1 squared, x2 squared will not be there anymore. Right. All right. So this is this topic. And next one is transforming features. So we can use a function transformer to transform data in your features matrix. For example, suppose we have a data set like this. So data are on very different scales, like 1, 10, and 100, 1,000, and 10,000, 100,000. So in this case, they are on very different scales. You can use apply some function on each column of the features matrix, right, by applying some function on it. So let's first import a function transformer, right, and then specify the function we want to apply on the feature matrix. Suppose that we want to take log 10 of all of the values. Then this is the instantiation of the transformer. We can call it log 10 transformer, and then transform the feature matrix. Get the result. Now they are on the same scale. Of course, you have to make sure that this transformation is legitimate. Okay? It makes sense. You cannot just randomly take a log of everything. So this is just a one way, one option for you. And alternatively, you can use the apply function in Pandas. So now we have a new features matrix like this, okay? And before you apply a Pandas function, you have to convert your feature matrix into a Pandas data frame first, okay? Because, you know, we have learned before, like different objects in Python have different methods associated with them, right? And Pandas functions are only associated with Pandas data frames. So similar, this is associated with Pandas data frame. That's why we first use the data frame function to convert the feature matrix. This is a NumPy array by itself, convert it to a Pandas data frame. Specify the column names, call it df, and then you can apply a specific function on the data frame. By default, it will apply it on each column of the data frame. So this is the result. This is similar with the feature transformer function in Scikit-learn. And next topic is detecting outliers. So in introductory level statistics, you probably have learned this 1.5 IQR rule. It's just one of the strategies to identify outliers. So using this rule, an outlier is defined as if it's smaller than Q1 minus 1.5 IQR or greater than Q3 plus 1.5 IQR. IQR is Q3 minus Q1. So this is just a very commonly used strategy or rule, and it is not the only rule, of course. And for example, in a box plot, usually outliers are identified in this way. If there is an outlier, if you use a box plot to plot the data, the outlier will be denoted by asterisks usually, and usually the box plot will use this kind of IQR rule, okay, 1.5 IQR rule. All right, now let's simulate some data using make blobs, okay? And we will simulate some bivariate data. Okay? Oh, 10 observations, 2 features, okay? Center equals 1, so only one group, a random state. Okay? And then we intentionally change 2 observations, make them very big, like make them extreme values, 10,000. So data created using functions in Scikit-learn data sets part, like make blobs or make regression, etc. Data are very regular, should be very regular, no outliers. That's why we need to create some outliers by ourselves. And then, okay, so feature 1 is the first column, feature 2 is the second column. And remember, we have 2 outliers. So now let's create a function to identify the index of outliers. So this is just a regular function. We call it indexes of outliers of some vector. And we first calculate the first quartile and third quartile using the percentile function. Right? So this NumPy's percentile function can be used to find quartiles, right? Percentiles, 25 and 75. And then calculate the interquartile range. And then set the lower bound and upper bound. Q1 minus 1.5 IQR is the lower bound. And then Q3 plus 1.5 IQR is the upper bound. And then we will use this where function to return the index, the row index of the value that is not within this region. Okay, so if it is smaller than the lower bound or greater than the upper bound, the lower limit, upper limit, then they are considered outlier. So this where function will return the index of those outlier values. So we first feed feature 1 to it. Feature 1 is the first column, okay? And turns out that it correctly identified the outlier. Okay, remember 0, 0, feature 0, 0 is 10,000. It's indeed an outlier, right? Using our rule, definitely an outlier. And if we feed feature 3 to it, it identified that it's the fourth value. Okay? The index is 3. Let's see. That's correct. Okay. For the second feature, the third value, the fourth value is an outlier. For the first feature, the first value is an outlier. So this is just this just shows you an example that you can write your own function to identify outliers or some other observations in your data set with some certain features. All right. Next, handling outliers. Whenever you identify some outliers, you have different strategies. First, drop outliers. This is the easiest way, but may not be the best way. And second is mark them as outliers and include it as a feature. So basically, you create an additional variable, a flag variable to flag outliers. Probably a binary variable with true or false values or one or zeros. Right? If it is an outlier, then one, otherwise zero. Right? And the third strategy is transform the feature to dampen the effect of the outlier. Right? So this, you should be very cautious if you choose to use this. Right? Make sure that it is reasonable to transform the entire feature to dampen the outliers. Let's create a small data set, data frame called houses, 3 columns, price, number of bathrooms, and square feet. So apparently the last observation has outlier values, like square feet and number of bathrooms. So very large numbers for both variables. So first we can drop outliers. If you are sure that the observation is due to some error, then you can drop it using conditional selection. And it's the simplest way, but may not be the best way. Yeah. And you can also mark them as outliers. Basically, you create a new column that will be used to flag outliers. For example, we can just add a new column called outlier, and then compare, use this kind of condition to assign the value. If bathrooms is less than 20, then 0, which means it's not an outlier, otherwise 1. So let's see. So after we run this chunk, then a new variable is created at the end, which is used to flag outliers. The last one is an outlier. By doing so, when you fit a model, for example, a regression model, you can keep this observation in the data set, because the last column will help you to absorb some kind of variation in the model. Right? So this one can help you to regularize the model somehow. Not regularize, to normalize the model a little bit. Okay? Because this is a variable, it will contribute to the fitting result. Okay? And the last one is to transform the feature to dampen the effect. For example, we can apply the natural log function on each feature of the data on the square feet only. Call it log SF. So basically, we create a new column called log square feet, and it is a natural log of it. Then you see that the last value is not that different from the previous regular values anymore after taking natural log. Of course, if you do this, you probably need to drop the original column and only keep this one in the data set. And you have to deal with the bathrooms, the outlier value in the bathrooms column as well. so that is another story. But anyway, this one is just an example. You have the option to dampen the effect of outliers by doing some transformation. So there is no hard and fast rule for handling outliers. It's really a case-by-case problem. So you first need to know what makes them an outlier. If it is due to errors, then you can drop them or use missing value and AN to replace them. And also how to handle outliers should be based on our goal for machine learning. All right. Any questions? Next is discretizating features. So basically, create discrete numeric variables using continuous numeric variables. Sometimes it's useful too. First, binarize data. So set feature values to 0 or 1 according to a threshold. Sometimes it's useful. People like binary data a lot. So to do this, we can use the binarizer function in the preprocessing submodule of scikit-learn. So let's first create an array called age. Again, it is just for illustration purpose. We create a very small data set. And then create a binarizer. You just need to specify the threshold, for example, 20. If the threshold is 20, then after you apply the binarizer, if the value is less than or equal to 0, 20, it will yield 0. It will turn 0. If it's greater than 20, it will yield 1. So let's see. Big transform age. So indeed, 6, 12, and 20 will be transformed to 0. Okay? Because 20 is still less than or equal to 0. It's equal to 0, 20, so it's 0. Okay? And 36 and 68 are greater than 20, so they will be transformed to 1. So this is called binarizer. We transform a numerical variable, a continuous numerical variable, to a binary integer variable, 0 and 1. Just need to pay attention to the threshold, how the threshold is defined. So great, we draw a line. This is 20, including 20, 0, 1. Okay. And then let's move on to the next topic. Sometimes you want to break up a numeric feature according to multiple thresholds. In this case, you can use NumPy's digitize function. So you just need to specify the thresholds for all of the intervals. But in this case, just pay attention to the definition. If x is less than 20, strictly less than 20, 0, greater than or equal to 20, and less than 65, 1. Otherwise, 2. So this function digitize is a NumPy function. Right? So the thresholds and how to use the threshold to cut the values is kind of different. So we have specified 2 thresholds, 20 and 65. So it's somehow like this. 20, 65. Because there are 2 thresholds, we will create 3 values. By default, 0, 1, and 2. 0, 1, 2. So from 0 to 20, from 20 to 65, from 65 to infinity, 0, 1, 2. It's slightly different from the definition when we use the binarizer function. Okay. All right. Let's run this. 0, 0, 1, 1, 2. So now 20 is in the second category, second interval. So it's coded as 1 instead of 0. And 68 is in the last category. All right. Missing values. If we have missing values, if we only have like a few observations, we can choose to delete them. Right? Delete them. One way is to use this kind of syntax. Tilde np.is none feature. So this will remove any observations with any missing values in any column. Right? So x is equals 1 means along the rows, yeah. So see, and then the last row will be deleted. So that's why I was kind of I was a little bit kind of slow because in NumPy, x is equal to 1 means row, right? And x is equal to 0 means column. In Pandas, they are defined in the opposite way. And in the last slide, notice that we are using a NumPy function. So this x is equals 1 is corresponding to rows, right? We'll delete rows instead of columns, give rows. So we'll delete all the rows with any observation, with any missing value in any feature, any column. All right. Now, alternatively, we can use a pandas function to drop any observations with any missing values. The function is just called drop NA. Just pay attention again, this drop NA method is associated with pandas data frames only. So that's why if we want to use it, we need to convert our NumPy array, the feature matrix, into a data frame. We just call it data frame, and then apply the drop NA method. Then you see the last row is dropped. Just pay attention to this. Whenever you use this function, you need to make sure that the missing value is coded as a valid missing value. If the missing value is coded in other ways, for example, coded as an asterisk or certain numbers or something like a letter, right? Then this function won't work. It won't help you to remove those missing values as you want. All right, let's quickly move on. So most machine learning algorithms cannot handle any missing values in the target and feature arrays. So for this reason, whenever you have missing values in your data set, you cannot ignore them. You have to handle them. Right? You can delete them. You can impute missing values using some other values, some strategies. Okay? So before we decide how to handle missing values, let's try to understand different types of missing values. There are 3 types. First, missing completely at random, MCAR. So the definition is, in this case, the probability that a value is missing is independent of everything. It is completely random, purely random. Right? Let's use one example. So for example, a survey respondent rolls a die before answering a question. If she rolls a 6, then she skips that question. So there is a 1/6 chance of skip a question, and it does not depend on anything. It just depends on the result of rolling a die, a fair die, right? And it's completely random. So this is called missing completely at random. In this case, usually it's safe to just delete the observation. And the second is missing at random. The probability that the value is missing is not completely random, but depends on information captured in other features. So the probability is not random. However, the reason that it is missing, this information is captured in other features that we have already collected. Right? For example, a survey asks about gender identity and annual salary. Gender and salary are 2 variables in the features in the survey or data set. Right? And we know that women are more likely to skip the salary question because of some reason, because they are they are more likely. And this totally rely on the gender identity. And fortunately, we actually collect this information, gender identity. So in this case, the missing values are called missing at random. So basically, in this case, we can use other features to capture the pattern of missingness of other variable, like salary in this case. And the last one is the worst one, missing not at random. The probability that the value is missing is not random and depends on information not captured in our features. So in the same survey, we know that salary women are more likely to skip the salary question. However, unfortunately, we didn't collect information about gender identity. So in this case, the missing values are called missing not at random. Although we know that the missingness, the probability that the values are missing, and also the values themselves depend on gender identity, we don't have information about gender identity. This is called missing not at random. So sometimes it's acceptable to delete observations if they are missing completely at random or missing at random. The first two cases, it's fine to delete them. Right? But for the last case, missing not at random, we should not remove them directly because removing these observations will introduce bias to our data set. So because they are produced by some unobserved systematic effect. So we will miss that. All right. Now let's take a look at strategies to impute missing values. So assume that we don't want to delete those observations. We're not sure what type of missing values we have. Then we can choose to use some other values to replace missing values. So this is called imputation. There are two main strategies to replace missing values. One is to use machine learning models to predict missing values using other features. Right? A commonly used one is k nearest neighbors, KNN, k nearest neighbors. So KNN use k nearest observations according to some distance metric, usually Euclidean metric, to predict the missing value. So the underlying theory is that observations that are close to each other, for example, we have observations, two-dimensional data like this, right? And for example, this data point has a missing value in some feature, right? Then because these observations are very close to this data point, right? We can assume that their other feature values, the feature values are very similar, right? Even the value that is missing should be similar to the neighbors in a small neighborhood. Right? So this is a logic of KNN. We would learn how to fit a KNN model in module 4, supervised learning. But for now, we just use it as an imputer. Scikit-learn has this imputer, KNN imputer. It's very convenient to use. So let's first, again, generate some data. We use make blocks to generate 1,000 observations with 2 columns. Okay? And then we scale the data using standard scaler. I save it here, standardized features. And then we save the first column, first row value. I call it true value. Right? And then replace it by a missing value. Right? So we create a data set with a missing value. Okay? When we change it to a missing value. Okay? And then let's try to use KNN imputer to impute this missing value and see what happens. Okay? And we first instantiate the imputer. Right? You need to specify how many neighbors will be used to do prediction for the missing value. And the weights by default is uniform. That means, so in this example, suppose this is the data point we want to impute value, and the neighbor is 5. Number of neighbors is 5. Then if weights equals uniform, then all of these 5 points have the same influence on the prediction of the missing value. And later on, we can see other options. And then fit transform, let's see. So this is a true value. 0.873. Right? This is imputed value 1.96. Right? So it's quite close. Right? It's quite close. We have tried our best. And notice that if we use KN imputer, you always feed the entire features matrix into it. You see, no matter no matter there are missing values in a column or not, we always directly feed the entire matrix into it, because this KN imputer will try to impute each missing value in each column with other columns, the rest of columns. For example, if you have a matrix like this, right, with a lot of columns, right, and you have a missing value here and a missing value here, right? And if you feed this entire matrix into the KN imputer, it will impute this value, this missing value in X1, using all of these columns, right? And at the same time, it will impute this value using all the rest of the features as well at the same time, right? So it will try the best to impute your missing values, right, in any column. And as I said, by default, it will use all of the 5 neighbors in the same way, treat them equivalently. But you also have the option to let weights be distance. Then observations that are closer to the data point you want to impute value will have higher weight on the predicted value. Okay? So if your data is not very regular, right, for example, some data points are very far away, somehow far away, you want to use this argument, weight equals distance. Okay? And for us, the result is slightly improved, okay, 1.02. So previous one, we have 1.09. So it's, yeah, the error is smaller actually. Okay? And alternatively, we can use some column statistics to impute values. So if you use machine learning modeling, you are using other features to predict values in this particular column, right? Other features, right? But you can also choose to use column statistics in this particular column. Right? So the function is called simple imputer. Use a single value. For example, let's create a new data set. Not actually the same data set. Okay? Still, we replace the first value by a missing value, right? And then we can instantiate the simple imputer using strategy equals mean, which means we will use the column mean to replace the missing value. Right? We fit and transform the features, and let's run this. Okay? So this is the true value. This is the imputed value. The performance is very good, very good. So apparently, that is because we use make blobs to create the data set, the feature matrix, and the data are very regular, basically normally distributed. So the mean is actually a very good representation of the entire column. Okay? So let's calculate the mean of the original features matrix with the missing value is -6, exactly the same with the imputed value that we use to replace the missing value. So indeed, it used the mean of the non-missing values in the column. If you think the data is skewed, you can choose to use other strategies. For example, you can use median. Okay? If the data is skewed, then median is a better measure of center, right? And then we can create a new imputer and fit transform, do the imputation. And apparently for our toy data set, the performance of median imputer is worse than the mean imputer. Yeah, again, it's because the data is very normal. And we can check the median of the non-missing values, exact the same with the one that we used to impute the value. All right, that's all for today. Do you have any questions? All right. We have no questions tomorrow. We'll continue to talk about handling categorical data, and then you will have a quiz starting at 10:30. It will be available on Canvas at 10:30. So, all right. See you guys tomorrow. Bye-bye. All right. Good morning, and welcome to today's class. Today we will talk about the last session about data management, handling categorical data, or how to pre-process categorical data. It is often useful to measure objects in terms of their quality instead of quantity. The variables that are used to measure these features of some individuals are called categorical variables. For example, gender, color, brand of cars. So these are all categorical variables, right? And there are two types of categorical variables, nominal and ordinal, right? For nominal categorical variables, the categories are nominal. So there is no intrinsic order between or among the categories. For example, colors, right? Blue, red, green, etc. Right? And also types of fruits, banana, strawberry, apple. So if there is no intrinsic order among the categories, then the variable is called nominal variables. And the other type is called ordinal variables. Okay? When the categories of the variable has an intrinsic order, for example, low, medium, high, young, old, gray, neutral, disagree. Okay? So it's kind of important to determine which type of categorical variable a variable is, because it will be related to how to encode these variables, how to encode the categorical variables into numeric variables. And machine learning models often require that the input to be numeric values, especially in Python, Python packages. The models always assume that the inputs are numeric values, so they just cannot accept any character strings. In that case, before we feed our data into the model, we have to encode categorical variables into numeric variables. And also how to encode these variables, it really depends on what type of categorical variable we have. Okay? And of course, in the process of transformation, we'll try to retain the original as much as information as we can. For example, for ordinal data, we'll try to keep this information, like the ordering among the levels. Okay? For nominal data, there is no intrinsic order, then we probably, we have to transform them in an appropriate way too. Okay, so let's see. So first, let's take a look at nominal categorical features. Okay. One way to, so for nominal categorical variables, we will just create dummy variables, right? Basically binary variables, 1 and 0s, for each category of the variable. So for example, if there are C levels or C categories for a variable, then we will create C dummy variables. Or sometimes we say C minus 1 dummy variables. But in Python, it doesn't matter that much. Actually, the redundant dummy variable will be ignored during the fitting process. And one way to one-hot encode or creating dummy variables is to use scikit-learn's label binarizer. So this is one way. So we first need to import the function, a label binarizer, from this pre-processing submodule from scikit-learn again. And we create a small toy data set called feature with only one column. So you see the values are character strings. They are states in the US. Okay. So definitely they are not ordered and no intrinsic order among them. So this is a nominal variable. So we first need to, again, instantiate the encoder or the transformer. We just use the default parameter values. Call it one hot. And then we can apply the fit transform method to encode the feature matrix. So, and save the result in feature T, which stands for transformed feature. So let's run this. So see, 3 columns of dummy variables are being created. So that is because in our data set, there are 3 levels, 3 unique values, Texas, California, and Delaware. So it really depends on how many unique values are contained in our data matrix. And the logic is like this. By the way, automatically it orders the values alphabetically. So the first dummy variable is corresponding to California. So if a row, if an observation is corresponding to California, then it will be 1, otherwise 0. And the second column is the dummy variable for Delaware, and third one is for Texas. So California, Delaware, and Texas. So let's verify it. So the first value is Texas, right? Then the first row in the new data matrix is corresponding to the first observation, Texas. And indeed, the third dummy variable is equal to 1. The first 2 are equal to 0. So this means this is corresponding to Texas. And second row, the second observation, C is equal to 1, California is equal to 1, right? So that's because the second value is indeed California, right? And D and T are equal to 0. So this is called one hot encoding because it's kind of like a switch. Dummy variables are kind of like switch, either 0 or 1, right? So for each, after the transformation, for each row, only one of the dummy variables is equal to 1 always. Right? You see, if you observe all of these, only one of them is equal to 1. So that means only one is hot. The rest of them are cold. 0 means cold, 1 means hot. So this is one hot encoding. Then, so we can use the classes attribute to output the classes. Namely, you can take a look at the ordering, the actual ordering. So it's California, Delaware, and Texas. So it must follow a way to order the dummy variables in the transformed feature matrix, right? So this is a default ordering, alphabetic order. And you also have the option to reverse the one-hot encoding. So namely, you can convert the transformed feature matrix back to the original features matrix. As you see, you can use the inverse transform function to convert it back to the original vector. All right. Another way to one-hot encode these nominal categorical variables is to use the Pandas package. Okay, so import Pandas as PD, and then you can just call the get dummies function. So let's run this. We will use this function. So then we have this. This is the new features matrix. So you see the underlying logic is the same. It will create a dummy variable for each unique value, for each distinct value in the original features vector. And also the dummy variables follow this alphabetic order, California, Delaware, and Texas. And personally, I prefer this function because it automatically creates column names in the result in the new features matrix. And also the result is a data frame. So it's very convenient. You can calculate some summary statistics using this data frame, using the pandas, using the functions in the pandas package. So it's kind of convenient. And then let's move on to the second type of categorical variable, okay, ordinal categorical variables. For example, the Likert scale, okay, strongly agree, neutral, disagree, strongly disagree. Okay? Apparently, there is an ordering among the categories. Okay? So when we encode this kind of ordinal data, we try to retain this information. We don't want to lose this information because they are kind of linear. Okay? It's kind of very useful. Okay? At least monotone increasing. Okay? May not be linear. So in order to keep this ordering information, we can create a mapper. Okay? A mapper is actually a dictionary. We know how to create a dictionary, right? So we can, if you want to do it in a very flexible way, okay, you have the full control of how to convert your your ordinal data into specific values. If you want to have a full control, then use a dictionary to do the mapping. And let's see one example. So we create a small data frame with only one column, which is score. So this variable only has three levels, low, medium, and high. So they are all strings, right? And suppose we want to convert these letter scores into numeric scores. So one way to do it is to create a dictionary. Okay? We can call it a mapper because we will use it to map string values into numeric values. So it's just a dictionary. A dictionary is a set of key value pairs. So the keys are corresponding to the original string values. So see low, medium, and high. And then you can decide which numeric values you want to convert them to. For example, I just convert them to 1, 2, and 3. Okay? And don't forget the comma to separate them. Okay? So we can call it scale mapper. Okay. And then we can use the replace function to replace the values. Okay. Remember, we have seen this function before, right? The replace function. It will replace the original value with a new value. Right? Remember, we used to use a missing value to replace all the male characters in the sex column in the Titanic data set, right? So now we just defined a mapper, right? How to do the replacement. Right? Replace low by 1, and medium by 2, high by 3 for all of the values in this column. Okay? So now let's run this. You see this is a result. Okay, 1, 1, 2, 2, 3. The original one is low, low, medium, medium, high. So after the transformation, we have 1, 1, 2, 2, 3. The first column is row indexes, so don't be confused. But it is a very flexible way to convert ordinal data into numeric values. Alternatively, we can use this function, ordinal encoder function, in the preprocessing submodule. Right? So for nominal data, we use one-hot encoder, right? But binarizer, high binarizer. But for ordinal data, there is a corresponding function too. Okay? So we can instantiate this encoder, just leave it open, so use the default options. And then just you can fit and transform. You can also fit and transform at the same time. So let's see what happens. So apparently it does not look very correct, right? So we have low, low, medium, medium, high. Right? But they were encoded to 1, 1, 2, 2, and 0. Apparently, by default, it will use 0, 1, and 2. But clearly the ordering is not correct. So it turns out that by default, it used the alphabetic order, alphabetical order. So it's order the levels like high, low, and median. So convert high to 0, low to 1, median to 2. Right? It's apparently wrong. Right? So we cannot leave it open. Okay? We cannot use a default option. So instead, we can specify the true ordering. You can do this, specify the categories arguments in the encoder, right? Specify the true ordering, right? From low to high. Okay? Call it ordinal encoder 2 and feed and transform our data frame. Okay? So now we have the correct transformation. Right? All right. And if we use this kind of encoder, it's kind of very convenient but very rigid because the numeric values are chosen for us, right? So the function uses 0, 1, 2. Okay? Imagine if you have 4 levels, then it will use 0, 1, 2, 3. Right? So it assumes that there is a kind of the difference between any 2 adjacent levels is the same, is 1. Right? So it's kind of a linear pattern. If this is not true, then we need to go back to our manual way. Okay, for example, suppose our data frame has an additional level called barely more than median. Right? So the data frame looks like this. There is a level like this. Right? Apparently, it won't be very intuitive to use an integer in between median and high. Right? Just one integer. Like if you code it like 0, 1, 2, 3, then you assume that the difference between median and barely more than median and the difference between median and high are the same, which does not make sense, right? So in this case, we should not use the Arduino encoder directly. Instead, we should create our own mapper. For example, we can transform this level to 2.1 instead of 3. So then we can encode it in the way we like. Okay. All right. And so this is one hard encoding. And notice that even if we use the replace function, the original data frame will not be changed. Right? So for example, if we type this, even after the encoding process, the values are still the same with before it is encoded. Right? So that is because, as I said, in Pandas, it always create a new copy of the data frame. If you do anything to a data frame, it will create a new copy, but the original one will not be changed. If you want to save the new copy, you can save it. Alternatively, we can add an argument in place equals true. Then it will change the original data frame. So let's see. So for example, we can add this, and then let's type this to see if there is any change. It has been changed. This is not always recommended, as I said. We'd better keep the original data frame intact. And if we want to save the result of any operation, just create a new data set, create a new data frame, save the result. All right. Next topic is imputing missing class values. In last lecture, we learned how to impute numeric values, right? So now let's take a look at a categorical data if there is any missing value. So one solution is to use the statistic to replace the missing values. For categorical data, the most intuitive one is the most frequent value in the column, or the mode, the most frequent value, because for categorical variables, the mode has the most frequency, and it is supposed to be the most representative value among all of the values. So it makes sense, right? So this is kind of like a simple imputing method. And still import the simple imputer function from the impute submodule of scikit-learn. And then let's create a toy data set so the first 4 rows do not have any missing values. And the last 2 rows has a missing value in each row. So see, have a missing value in each row. And then we stack them together. I vertically stack them together, call it X complete. The reason that we create them separately is because later on we will use machine learning model, basically k nearest neighbors to impute the values. In that case, in the training part, in the fitting part, we can only feed a complete matrices into it. Okay, so it's not the KNN imputer anymore. Okay? It's a classifier. Okay? It's a real classifier. Okay? So we'll see a little later. But anyway, don't be surprised. You might be curious why we created them separately. Okay? There is a reason. Okay? So anyway, this is a complete data frame, okay? Feature matrix. Then instantiate the imputer. Okay? Simple imputer strategy is most frequent, which means the mode. For numeric variables, we use median or mean, right? But for categorical variable, we use most frequent. I just call it imputer and feed transform our data set. And then you see that 1 is used to impute the missing values. That is because you see among these 4 values, right? 1 is the mode. 1 has the biggest frequency. 3, 1, and 0, 1, 0. So definitely we should use 1 to impute the missing value. So this is the simple imputer. Alternatively, we can use machine learning models to predict missing values in any column in the data frame, right? So instead of using KNN imputer, because the KNN imputer last time, the imputer that we learned last time is designed for numeric values only, numeric data only. It cannot be used to predict labels, right, or categorical variables. So we will actually use the machine learning model like k neighbors classifier, so to do prediction. So to do it, we first need to instantiate the classifier, the function. Oh, by the way, the function is from the neighbors submodule in scikit-learn. And we instantiate it. So we use 3 neighbors this time. So k is equal to 3, and weight is distance. And then we can fit the model. Again, as I said, most machine learning models, actually all machine learning models, cannot take missing values directly. Forget about KNN imputer. Okay? So that is not a machine learning model. It is a imputer that uses a machine learning model. Right? So that one can accept missing values because it is used to do that, to impute values, right? But a regular machine learning model in Python will not accept missing values. So that's why when we create the features matrix, we separate them, right? One part does not have missing values. The second part has missing values. Right? So notice that we only feed the first matrix to it. Right? And also when you call a machine learning model, you have to separate the features matrix and the target column. Right? So the first argument is the X matrix. The second argument is the Y vector. Right, so notice that when we create them, they are together. Right, so this is this is the column with missing value, which is the first column. Remember, the first column has missing values in the second part. Right? So we treat it as a target vector, right? And then train the model, and then we can do prediction for the part with missing values. Right, and pay attention. We just feed the part without missing value, which is treated as a features matrix. and then we can save the result in imputed values, right? Same result. If we use k and n, we get the same result, okay? 1 and 1. Okay? So the k neighbors classifier can help us to predict categorical values, okay, or factor values. Right? So it's 1, 1. And then we can do some more data manipulation. So we first make the imputed value as a vertical vector, and then horizontally stack it with the part without missing values. Right? So this is the kind of the second part without missing values with imputed values. Okay? Then furthermore, we can vertically stack the part without missing value and the part with missing value together. So this will be the complete feature matrix after the imputation. Okay? So it requires some work, apparently, because there is no k and n imputer for categorical variables in Python. Right? And alternatively, we can use it, right? But you see the imputed values may not be an integer because the response variable is assumed to be continuous numeric. So you can still do it, but you need to do some extra work. Namely, you need to round the result to an integer. Right? So the first imputed value is 0.88. If you round it, you will get 1. So you can round it to a whole number, so you get similar result. Yeah, I think it is in general okay. Even if you have multiple categories, for example 0, 1, 2, right? You can still use the kn imputer and then carefully round the result to an integer, right? Either 0 or 1 or 2, and then that will be your the best imputed values. Right? So either way is fine, but theoretically, you should not use this because this is for numeric values. All right. Then let's continue. Okay. As I said, I emailed you this morning. The quiz starting time of the quiz has been postponed to 11 a.m. And because I know that I cannot finish everything in 30 minutes, okay? So don't worry, okay? The quiz will be open at 11. You will have sufficient time to do it. All right. Then let's move on to the last part, handling imbalanced data. Sometimes the target vector is highly imbalanced, which means, for example, we have 90% of zeros and 10% of ones in your data set. Or there are more extreme cases, especially in the insurance industry. The probability of ones probably is just 0.1%, and zero is 99.9%. So highly imbalanced data. In this case, it creates a lot of difficulties in fitting a machine learning model and to have a high quality prediction. So especially for the smaller class, right? For the, for example, 0.1% class, it's very difficult to make good predictions because the sample is too small. Okay, it's too small. And how to manage this situation on highly imbalanced classes? Right? There are a few strategies. The first one is to collect more data. So if it is possible, we can collect more observations for the smaller class. But unfortunately, it might not be feasible in practice always. And the second strategy is to change the metrics used to evaluate your model. So we do nothing about the data, but we consider more metrics when we assess the model. So why do we need to change the metric? For classification problems, the most commonly used metric to evaluate this kind of model is the accuracy. And the probability of making a correct prediction, accuracy. However, if the data is highly imbalanced, for example, there are only 0.5% of observations have some rare cancer, and 99.5% of patients don't have the cancer, right? Which is very intuitive, right? Because it is a rare cancer. Right? In this case, even a very naive model can have a 99.5% accuracy. Why? Because you can just make a model like this. Okay? Given any new observation, predict that the person does not have the cancer, has that type of cancer. Then 99.5% of chances you are correct, because in the population only this many are healthy. They don't have that cancer. Okay? So accuracy won't work. It won't be a good metric to evaluate the model. So in this case, we should consider some other metrics that can evaluate your model in a more comprehensive way. For example, you can create a confusion matrix or calculate precision, recall, F1 scores, etc. Okay, so they and also ROC curves. So they can help us to evaluate the accuracy in the small classes in a more effective way, a more precise way. And the third option is to use the class weighing parameters included in some models. Right? Some models have this argument, class weight, this parameter. You can set it to be true, to be equal to balanced. Then in the process of model fitting, they will try to increase the weight of the smaller class and decrease the weight of the larger class, okay, so that the result will be more balanced. Okay. And the last two strategies are downsampling the larger class or upsampling the smaller class. So these are kind of manual ways to handle this imbalanced class situation. So let's take a look at downsampling. So in downsampling, we create a random subset of the majority class of equal size to the minority class. So for example, we have 100 observations of 0 and only like 10 observations of 1. Okay. So in downsampling, we will draw a random sample of size 10 from the larger class, okay, and then combine these two together to have a perfectly balanced data set, and then fit the machine learning model. So this is called downsampling. Of course, this is not a good idea because we will waste a lot of observations in the larger class. Right? We shrink the sample size, which is in general not a good idea. And upsampling, the opposite. Right? So again, we have 100 zeros and 10 ones. Right? In this case, we will do resampling of the smaller class with replacement, and so that the sample size is equal to the larger class. Right? Resampling. So in this case, we must allow replacement, right, so that we can essentially enlarge the size. But pay attention, the variation won't be changed. Right? So this is another way. Right? And there are some examples. There is one example about it. So let's finish this part. We will use the iris data set. So this one contains 3 balanced classes of 50 observations. So 3 classes, each one has 50 observations in the iris data set. 3 classes, completely balanced. Right? And we will manipulate the data a little bit. Right? We will get rid of the first 40 observations for class 1, the first class. Right? So then consequently, we only have 10 observations for the first class. And we also will combine the second and the third class together so that we have 100 observations in the second class and code it to 1, and this is 0. Originally, these are 0, 1, and 2. Right? We combine them together to get 1, right? So that we create a imbalanced data set. Right? So this is what we do here. Right? So see, we import the iris data set and load the features matrix and target vector. And then we subset the features matrix and target vector, right, by starting the index from 40 and then to the end of the data set. And so basically we got rid of the first 40 observations, right? And then we recode the target vector. You see, we use a where function. So if target is equal to 0, then 0, otherwise 1. So namely, we combine the second and third classes to 1, right? So that it's a binary problem after this step. Okay. And then I see how to do let's skip this, how to do downsampling, right? So we first save the indexes of zeros and ones in I class 0 and I class 1. Right? So you see, we use this conditional to select the indexes of these observations, these target observations. Right? So I class 0 basically are integers like 1, 0, 1, 2, 9. Okay, actually, and I class 1 will be what? Will be 10, 11, all the way to 109. Yeah, so totally 100 indexes for class 1 and 10 indexes for class 0. And then measure their length. And class 0 will be 10, and class 1 will be 100. Okay. And then we use this random choice function to select 10 indexes from I class 1. Okay. So basically, select 10 numbers from this set. Okay, replacement equals false because we are doing downsampling. Okay, we are sampling 10 from 100 indexes, so we don't allow replacement. Okay. Then save it in here, I class 1 downsampled. So this set contains the indexes that we will that for the downsampled class 1. Okay, downsampled class 1. And then we can use them to choose observations for class 1 target values, right? And combine them with class 0, original class 0. So 10 plus 10. So now 20 indexes. Right? And next, we can use them to select features, the rows in the features matrix, and then combine them together. Oops, sorry, I forgot to run the previous code. So see the indexes, the target values for the new data set. It's completely balanced now. And also then, so we vertically stack the features matrix for the class 0 features and class 1 features. Right? So these are the first 5 rows. Right? So this is downsampling. Upsampling works similarly, but so now we will choose from I class 0. I class 0 is what? Is the small set 0, 1, all the way to 9. Okay. So size is equal to n class 1. N class 1 is equal to 100, remember? So we will sample 100 indexes from this small set of 10 indexes. Of course, we need to let replace equals true. Okay, so this is called resampling. Okay, so we manually increase the size. Okay, and then we can, so you see, after we do it, so this is the new target vector, like 100 zeros and 100 ones now. Okay, because we resampled, yeah, 10 times. Right? And similarly, we can vertically stack the 0 class, the new 0 class features and the 1 class features. So now the features matrix will have 200 rows. Originally only have 110 rows to 200 rows. We enlarge the smaller class. All right, perfect. I think we can stop here.